Hi folks, and welcome to another episode of Open Analysis Live. So it's 10 o'clock on a Saturday night. Do you know where your reverse engineering friends are? Right here behind the debugger. So I had some free time tonight and I thought I would play around with a new debugger. I'm always getting for using Anti-debug from my friends and my colleagues, and I use Ollie most of the time if I need to use like a good debugger, but Ollie's kind of old, and I've been hearing a lot about these new debugger set, x32dbg and x32dbg. Everybody seems to think that this is the future, so I figured I'd give them a try and see what they're like. So what I wanted to do was just kind of see if I could unpack something kind of quick with it, see how it compares with Ollie, which I'm most familiar with in terms of a non-IDA debugger, and how it compares to IDA. Obviously nothing's quite as good as IDA in my opinion, but I'm sure I'm going to get so much hate for that in the comments. But yeah, anyway, so I figured I'd give it a try. So what I wanted to do was take a look at the GlobeImposter ransomware. So recently, Brad had a quick note about this on his blog where he took a look at a recent GlobeImposter sample. And if we scroll down here, he's actually got the sample listed here. So we can use our nice OAPivot plugin and see if there's actually any analysis of this actually already been submitted, and there has. So there's already analysis of this submitted to hybrid analysis, so we can just take a look at it here and scroll down and see what the process tree looks like for this guy. So it looks like it runs itself a couple times, so it might be some process injection or something like that. And if we take a look at the screenshot here, we can see it looks like some of these files like Minesweeper have been replaced with a document, and there's a readme file here. And I did take a look at a blog where somebody had looked at GlobeImposter before, and it looks like it drops, I mean, it's ransomware, and it encrypts files, and then it drops a readme in each directory where they tell you how to get your files back, pay them some Bitcoin or whatever. What I wanted to do was grab that sample and then load it up in a VM here. And so here we go. I have the sample copied over already, and what I've done, because I know this is ransomware, is I've turned off network connections and I've turned off shared folders, so this VM is completely isolated, and that's the way that we're going to be working with it today. So I think I'm just going to load it up and see what this thing looks like. Now I was doing a little bit of practicing earlier just so that I wouldn't be stumbling too much. I do actually kind of like the debugger. It's nice. It has some features that are nice and similar to Ollie, so it doesn't seem too crazy to jump into it. And there's a few other extra things like the show graph stuff that I'll show you guys in a minute that I think is pretty nice. Okay, so let's open up our sample here. It's on the desktop, globeimposter.exe. We'll open it up, and the way that it works is x32dbg will automatically set a breakpoint on the entry point. So if we go and look at our breakpoints here, we can see they've already set a breakpoint on the entry point. So if we want to just jump to where the breakpoint is, we just double click on it and we're brought in here. Now with this program, they're using a bit of setup before they get into WinMain. So what we're going to do is we're going to have to actually, because this isn't actually where the code starts, the user code, this is all just setup stuff. What we're going to do is we're just going to actually jump over into graph mode, and this is one of the cool things. So you can kind of see it's almost like an IDA-like graph layout. It's much easier to see the code flow here, and we'll kind of go down to near the bottom of the graph here before they return. So before they get into the return, one of these calls is going to be to WinMain, and I know that it's this one right here because we can see being pushed onto the stack here is the base address of the module. Module is loaded at 4 and 5 zeros. So I just know that. If you were unsure about this, you could look up the definition for WinMain. This is actually an instance handle, which really just means like the address of the base of the module. So the best way to find WinMain is just to look near the bottom of the function before they return, look at the calls, and then see which call has the base address of the module being pushed to it. So we can see it's right here. So we can just double click to go to it. And the cool thing here is like they show it to you in graph mode, but you can actually right click and then do follow into disassembly, and you can pop over here. So this is actually WinMain right here. And there's a neat function here. You can do analysis and you can do add function. So that actually adds a function definition here. And this is actually our WinMain. So why don't we put a breakpoint on here? There we go. And so now we can just run. So it's hit the entry point, and let's run again until we get into WinMain. Okay, I did that kind of quick, but really all you're doing here is if you're used to using the IDA debugger, or if you're used to using OALabs, this is just the entry point to WinMain. So we're sitting in WinMain right now. So let's pop back over to the graph view and we'll take a little bit of a look at this actual function here. So we can see something interesting. One of the cool things about x64dbg, I'm going to mess this up all the way through the video. So So there's two debuggers, one for 64-bit and one for 32-bit. I'm just going to call it x64debug because that's what everyone calls it. This is actually x32debug, the 32-bit version of it, but don't mind me if I mess it up. You guys know what I mean. So here we go. One of the cool things that they do is they'll actually resolve the API call names. So these are all like Win32 APIs. And so you can actually see what's being called here. Now we kind of can see that this is junk code because it looks like they're just pushing a bunch of null values on and then calling things like win HTTP open. And I know that like when HTTP open actually takes a bunch of arguments that you need to pass it. So passing junk values like 000 isn't going to make any of these APIs do anything. So let's scroll past those and see if we can see something that's of a little bit more value. Again, there's more null bytes here. So one of the tricks here when you're looking at a packed sample is go down to the bottom of the function and see what they do before they return or before they exit. Because a lot of the times, if it's some sort of injection or some sort of, especially if it's some sort of self-injection, a lot of the times near the end of the function will actually be a jump to a register or a jump to a code segment. And that'll be, that's where you want to put your breakpoint. And it's usually near the bottom of the function. So with this graph view, it's really easy. We can kind of like scroll down. Here's a loop. Oh, there's something interesting here. Here's the end of the function. So here's their return and that's where they end. And we can see just a little bit above here, they have pushed a bunch of values onto the stack here. And then looks like they're calling virtual protect, right? So they're pushing virtual protect. You guys can see that written down here onto the stack. And I can see a call out to get process address. So probably what they're doing is they're dynamically resolving virtual protect. Now, for those of you who aren't too familiar with different packing techniques or unpacking techniques, usually if you are going to write code into a memory segment and then execute it, you could either create the memory segment with read, write, execute privileges, or you could create the memory segment. You can do an alloc. You can write the code there, and then you can change the protection of the memory segment using virtual protect. So here, I think that's probably what they're doing. So I'm very interested in that memory segment. I'm very interested to see what's happening with it. And I can see down here, there's a call to a memory segment, and down here, there's a call to EBP plus 14. So what I'm going to do is I'm going to add a breakpoint here, and I'm going to add another breakpoint here. Don't need to add the second one, but I'm just doing it to demonstrate to you guys that I'm interested in both of these addresses here. And then I'm going to run. So we ran and we got to this breakpoint here. You can see the little black mark beside the breakpoint. But if we go back into our CPU view, that's where we can actually see where EIP is. And anytime if you ever get lost here, it's kind of cool. You can just double click on EIP and it brings you right back to EIP. So we can see here now, one thing that's important here is you didn't see in the graph view, you didn't see that this memory segment was not repopulated based on what appeared in it currently. But if you go to the disassembly view, you can see that it's been repopulated or renamed to be virtual protect. So you should always just be following it in the disassembly view here. So we can see here it's been renamed. So this is actually a call to virtual protect. So they must have used the stack string here where they push virtual protect string onto the stack, and then they called get process address. And then you can see the return from get process address would be an EAX. They move that into this memory segment. And then of course this memory segment is being called here. So let's take a look at the stack and see what arguments they're passing to virtual protect. I have a feeling it's probably something related to this EBP here. So I'm thinking probably what they're doing is they're changing the protection level on a code segment so you can execute it. And then they're going to use this call EBP minus 14 to jump into that executable code segment. So let's just take a look at that. So if you guys remember, first argument is pushed last on the stack. So here is the actual address on the stack. So if you guys are wondering, how do I know that? Well, this is actually the stack view down here, and we can see the stack address is here. And then ESP is pointing to the stack address. So E70, E70. So that's our stack. So here's the address that we're actually setting the protections for. Here's the size, and then here's the protection value. And if you guys want to double check that, we can just open it up in a web browser here. Here's virtual protect on MSDN. So first argument is the address, then the size of the address, and then the new protection value. So let's go down and look at the new protection values. So let's look at the protection constants. So here we go. Depending on the value that you send in the protection constant, it's going to do a different protection for the memory segment. So what we're interested in here is execution, page execute read write. So this is full execution, and read write is 0x40. So if we go back to our stack here, you can see here is 40. So indeed they are turning this memory segment into executable code. Let's jump over that and we'll come down to the next point here. So now we're going to jump into EBP minus 14, and here we go. We've jumped into a bunch of code, and there's a second jump here. So let's just follow that jump. It looks like it's just jumping down a little bit to the next part of the code here. So we'll just jump down here. Now, the interesting thing here is this is a bunch of code that's been injected into memory, and we can see here the memory segment address on the side. So we're probably gonna have to redefine this as a new function. So we're gonna add a function, because we can see here push EBP, move ESP EBP, and then sub to make actually your stack space. So this is a standard function setup, a standard beginning of a function. So we can just rename that as a function. And then we could also, if we want to, take a look at it in the graph here. So here we have something interesting, because this is going to be probably shellcode or position independent code. It doesn't look like the unpacked version of a PE because it has all this kind of weird stuff in it. This looks more like sort of a stub that's setting stuff up. So let's kind of take a look at what they might be doing. We can see there's a couple strings here. It looks like a fairly big function. So let's kind of do a little bit of a walk with the debugger and see what they're trying to do here. Now, I'm pretty fearless because I'm in a VM and I'm running this VM completely isolated. There's a snapshot of it. So if I mess up, I can just revert it. So I find a lot of times, if you're kind of unsure about what's happening, it's pretty easy to just take a snapshot and then keep walking through the debugger. If you mess something up, you can always just go back and revert it. So I'm just going to do a couple step overs here. I see what I'm really interested in here is these call functions here. So I'm going to just step over until we get to the first one here. So if we look here, we can see a bunch of moves here, and that kind of looked like what we saw before in the rest of the function. There's these blocks where they're moving a bunch of D words over. So why don't we kind of jump down until we get to the beginning of it. Now, I know what this is because this is really common in malware. We call these stack strings. So basically, this is where you, instead of having a constant string in your malware, you push parts of the string onto the stack in order to create the whole thing. And then that way, if somebody runs strings on it or whatever, it's just an obfuscation technique, basically. I'm going to show you guys something kind of cool about x32dbg, where what we can do is we can sort of actually watch the string being built. So if we grab this right here, we can right click on it and do follow in dump, and we'll follow the address here in the dump. And that's going to actually show the address contents here. So watch as we execute down here. We have to get down to it. Okay, so down here we can see they've actually moved something in here. It looks like K null byte E null byte. So that's the D word that they moved in. So let's jump through a few more of these moves. We'll get down to the bottom here. Do you see something happening? So it looks like they're moving kernel 32 in wide strings. And remember, I've talked about this in a few other videos, but a wide string is really just an ASCII string that's been moved apart, and in between each character they've put a null byte. So because it's a 2-byte wide character string, that's what a wide string is basically. So here we have K null byte, E null byte, R null byte, etc., etc. And so it's kind of cool because you actually watch that string being built on the stack here. I think what they're doing here is they're probably trying to resolve some APIs dynamically. And because you would generally need to resolve your APIs before you do any anti-debugging tricks, I'm pretty confident that we can actually just run through this whole function without worrying too much about what it's doing, because it's probably just resolving APIs. And by doing that, we can check and see what APIs it's resolved at the end. So let's just do a run until return. And so here, I'll just show you, I'll scroll up a little bit. So here's a return. We'll just jump into it. And here we've just returned from this function. So one of the neat things that you might notice something's a little bit different. One of the neat things that x32dbg does is they'll actually add the labels to these addresses as you go. So you can see here, these two memory addresses that were actually pushed onto the stack before we called that function now contain the two APIs, load library A and get process address. Now here's the cool part. You can kind of scroll down here, see these stack strings. Remember, that looks very much like what we just showed you with the stack string. Look at what happens after the stack string. There's a call to load library, which we just resolved up here. And then there's more stack strings and a call to get process address. So probably what's happening here, most likely, is this is all API resolving stuff. So what's really cool is if we scroll down here, we can see these labels have been applied anywhere the memory address is called. And if we look at these they look like stack strings, like what we just described. So probably what they're doing is they're building strings and they're calling load library. That looks like they're probably trying to load a DLL. And then there's more stack strings and they're loading, they're calling get proc address. So they're probably loading an API. So this looks a lot like dynamic API loading. So what we can do is kind of come down till we see the last get proc address, and let's add a breakpoint here, and we'll just run until we get there and see what the labels give us. So see, this is really cool, right? So x32dbg has now relabeled all of these memory addresses with the APIs. So now that we have the APIs that they've dynamically resolved, we can take a look through them and see what they're actually doing, right? Like what sort of, so there's what is this shellcode doing? So virtual alloc, virtual protect, get version, lots of terminate process stuff, get procedure address, which we already talked about, output debug string, that might be an anti-debugging check, we can see in a minute. Yeah, so it looks like those are the only APIs that they have resolved. So in that case, it looks like there's probably not really any anti-debugging stuff in here, except maybe that output debug string. And I can actually link to below, I'll link to the cheat sheet that I have for anti-debugging techniques. I describe it in a previous video, and so actually I'll link to that video as well in case you guys are curious about it. But by looking at these APIs, I'm pretty confident that they're probably not doing a lot of anti-debugging checks here. So what I'm going to do is I'm going to jump back to our graph view here, and I'm going to scroll down, and I'm going to use the same trick I used in the previous stage, where I look at the bottom of the function and I look to see, do they change control by using a jump to EAX or jump to a register, or using a call to a register, or using a call to a memory segment, because that might tell me that this stub is unpacking to a new memory segment, and then we're going to jump to it. So let me just take a look down here. See, again, using this graph view, I really like it. I think it's awesome. I'm a super visual guy, so I like to see the control flow mapped out like that, and it makes it easy to sort of navigate and find the end of the function. So we're coming down here, and it looks like right at the bottom here they have this jump EAX. So again, knowing these common packing tricks, I know that I probably want to put a breakpoint here. Most likely this is controlling execution and it's transferring it over to another section of unpacked code. So I'm gonna just see if I can run until I get there. I do also want to mention something kind of cool that you guys might see here. You might have noticed. See how they're building another stack string here that says jump OEP? Now, that sounds a lot like jump original entry point. And I've noticed there's also other stack strings up here, like no PAT exit. And there's a couple other ones like MSV CRT. And I was definitely, when I was looking at this stuff, I was wondering, like, what are they actually doing with this? Like, why are they building these strings? These aren't API strings. What are they doing with these? So why don't I show you that quick? Because it's kind of interesting. And it also makes me question what they're doing with this packer. Like it seems like maybe it's in development or something. So why don't we do a right click and follow in disassembly here, and here we'll add another breakpoint, and we'll just run until we get to it. I think it's again, this isn't important for unpacking, but it's just something interesting that I noticed about this code. So we'll just run until we get here. Now, what are they actually doing here? Well, they're pushing this string jump OEP onto the stack, and then they're calling this function. So let's jump into that function and take a look at what it does. So I step forward a little bit, and you can see that x32dbg has repopulated this call here to output debug string. So, and then what they're pushing onto the stack is that argument that we passed to it, which is jump OEP. So what they're actually doing here is they're outputting those strings as debug messages. So it's super crazy. I'm not sure why they're doing this. And so if we jump over it, they've just sent that out as a debug message. And so if we look down here, we can see the debug string is jump OEP. I'm not sure, like, again, this is meant to send this message to a debugger. So it looks like this is maybe a debug build of the code. Again, I'm really not sure why they're sending all these helpful debug strings out here, but it's nice for us because we know that, here, let's just return from this. So we know that now we're going to jump to OEP. Isn't that weird? I think it's weird. So that probably means that this jump EAX is a jump to OEP. So let's just jump into it here. And remember, this jump EAX is the same jump EAX that I put a breakpoint on at the end of this function here. So it's the same one. And I guess they're telling us that it's OEP. So let's treat it as OEP. So we'll jump into it. And then we have this kind of interesting, call into another section of the code here. So we can jump into that. And what's happening here, what's kind of weird here is that was an immediate jump. Like that last instruction was an immediate jump. So I'm thinking probably this is OEP. I'm thinking there's probably just a one-stage hop into OEP. So here's the cool thing. Now, normally, like when I did this the first time, I didn't quite know what the debug strings were, and I was kind of confused about, what was going on. So I did actually look at some of this code. I kind of walked through a bit of it before I realized, oh yeah, this is actually the unpack code. But because the debug string tells us that we're jumping to OEP, we can kind of just treat it as OEP. So I'm going to show you something really cool about x64debug, x32debug is now that we've jumped to our OEP, we can actually just dump and reconstruct the PE file directly from the debugger. I think it's super cool. So they have this plugin here called Sylia, which is kind of like imprec, if you guys remember imprec. I don't know why it's not working. So something kind of embarrassing. When I went to run and show you that, the plugin actually crashed, but I reset everything. So that's why my debugging time is reset now. But anyway, no big deal. We're back to where we started. So now that I know that this is the original entry point, I can actually use this Sylia plugin. Sylia. I don't know how to say that. Sylia. It's basically like import reconstructor, like imprec and Lord PE combined. So it's like a dumper and an import reconstructor all combined. And it's super easy how you use it. So you basically just give it OEP. So we'll just grab right here. We're going to copy the address, pop back to our plugin here, paste the address in here. And then we're going to do an auto import address table search. So it actually found the import address table automatically. Okay. And then we're going to dump the file, and we'll dump it to something, dump.exe. Sure, save it. So that's pretty much all you need to do, and that should be a nice extracted dumped PE file. So why don't we load that up in IDA and take a look. So here we go. We've loaded it up in IDA, and it works like a charm. Here's our entry point right here. And if we look at our imports, we have all of the imports. These are all the nice dynamic ones that have been built for the unpack code. And if we just do a quick string search, and if we look at the strings here, we can see a bunch of strings that are related to GlobeImposter. Now, this is like a new version of GlobeImposter where a lot of the strings are actually encoded or obfuscated, but we can at least see here where they're deleting the VSS shadow copies so that you can't restore from the shadow copies. So there you go. Pretty quick tutorial. Hopefully it was interesting. I definitely thought it was kind of cool to get to play with a different debugger, something I'm not really used to. I think I'll probably be using it in the future. I mean, my heart is still with IDA, obviously. IDA debugger forever. But yeah, so whenever I actually do need a real debugger, I think I'm probably going to try and transition from Ollie over to x64debug. I think it's pretty cool. So what I'm going to do is, as always, I'll put a link to the sample below in the description of the video. I'll also put a link to the download page for x64 and x32 debugger. They're both free open source debuggers, so definitely if you want to give them a try, you can replicate what I showed you here today. And I'll also put a link to OAPivot, which is that Chrome plugin that you guys saw me use earlier to do a quick search on an indicator. So that might be of use to you guys. As always, keep sending us comments for what you guys want to see, what types of videos you want to see. We have a few queued up from some of the comments that you guys said earlier. So we're definitely going to try and get some of those videos out for stuff that you guys asked for. Also, remember to like and subscribe. New tutorial videos every week, one a week. Hopefully we can keep this up. And also make sure to spread the word if you like what you're seeing. So I guess that wraps it up. Keep exposing the mechanics behind the malware and stay curious.